So let's look at the retaining walls in here, see what it says about it. Here we go, retaining walls. Comprehensive range of features, including BS, EuroCode and Irish codes of practice design. So our main focus today is going to be on the EuroCode, EuroCode 7 for the application of loading, EuroCode 2 for the design of the concrete, and I think it's EuroCode 5 for the design of masonry components. So there's a lot of different codes of practice, although we did say EuroCode 7 in the trailer that came out to you. What I will stress now at this point in time is its gravity retaining walls. We're not doing sheet piling, retaining walls and stuff like that. We are doing gravity retaining walls. So let's go and have a look at the Master Series. I've already started the Master Series for you, and you'll notice that I'm using 2014-04. That is our most up-to-date version. It is on release candidate. It has been out to beta for the last couple of weeks, and it's now upgraded to release candidate last week. And I believe that we'll probably be starting to ship that to everybody end of this week, beginning of next week. So you can all phone on May Day and try and get tech support if you really want. Also, in this version I'm using, it's an X64. It's the 64-bit version of the Master Series. We now, with this latest release, have 32 and 64 bit releases of the Master Series. In the retaining walls, not going to make a difference. Finer elements, dynamic analysis, big frames, absolutely. You will get benefits in the size of frames and in certain areas, the analysis. So let's go in and look at the types of retaining walls. Designer Suite, retaining walls. And what I'm going to do is going to walk you through the different types of walls, the different materials, the different types of loading, and then we'll come back and do a bit of design. So I have this nice sample file, which hopefully I will give out to everybody afterwards as a wee email to install on their system and play around. I do not claim that every single wall here has been optimized. Most certainly they have not been optimized. They are created to demonstrate different components of the program. Some of them might even fail. So our most basic retaining wall. Designing the EC3 and the EC2. It's a reinforced concrete retaining wall with a reinforced base. There's the surcharge. That is the standard surcharge that you have for the software. You then have your stem and your toe and your heel. And we can see here it's very straightforward. It's telling us very simply that it all works. There's nothing in here that is showing us any failure, but I'm not going to go into that, and I'm going to go into looking at the different shapes. We will look at the design and the interpretation of the results in a later stage. So I have 12 different retaining walls here, which I will talk about. Retaining wall 2 is very simple. And if we move over to the second page, I have now the facility to say that I have a 100 and a 200 enlargement of the stem at the base. So as I change this value, 300, 400, 500, obviously we now get into problems with the minimum areas of steel, and come back down, and we can see we can taper the inside and outside of the wall. Quite popular is to actually put your taper on the outside, because if you make it vertical, people walking past it, if it's a sort of exposed, are going to think that it's coming towards them. So quite popular to put a small slope on the outside face. So it's very simple tapering. The next thing we can do, and I'm just going to use the buttons up here to move through the screens, is to put an extension onto this wall. So this is an extension, and we will see later on how we can apply loading onto that. Because it's an extension, in concrete, it will actually be reinforced, and if we export our results, which we will do later on, it will all come through. And the extension is just the separate input here, so I can pull that back down to say a meter if I wanted to, or make it higher. We don't have to have an extension, and we can get additional loading onto the structure, from a fence, from a railing, without putting the extension on, and we will see that later on again. Moving forward, we're now into keys. We're into shear key definition. Shear keys, in this case, it's continuation of the stem. I can move that about. I can make it such that it's at the front of the base, where it gets most of the passive, or I can move it to the back. Oops, sorry, that's the wrong button. This one here. And move it on the way back, or I can just go ahead and say, come on Tommy, let's get on with this. Let's type in a value 1800 and move it to where I want. The use of nibs is quite debatable. It depends on your passive soil, and it depends on the height of passive soil. And the reason for that is that you're taking a loading here that's coming around 25 kilonewtons, and it's quite high. Maybe it's only 20 at this point, so it's 20 and 25, so that'll be about 22 average. Whereas on this side, your resistance is coming in, okay, 28. Yes, the passive is higher, but it starts at 0 a lot quicker. So therefore, until you got a deep nib, you're probably not going to experience any net gain in sliding. I know it's a wee bit strange, but that's the way the code tells you. The code tells that you must apply on this side the soil pressures from the full depth of soil. So that's nibs for you. Very straightforward. The next thing I want to look at is getting very fancy, and we're into counterforts. Now, frequently counterforts might be in masonry. In this case, I'm just demonstrating the geometric shapes, so we're into reinforced concrete at the moment. And there's no reason why we can't do that if you so desire. And the counterforts, if we go to piers, as you can see, we have a different width at the top and at the bottom. And we can also put the pier on the other side. So the pier on the compression face, or the pier on the tension face. Preferably, if it's allowed, the compression face, but normally you want to hide it so it's on the slightly less effective tension face. And that's very, very simple. And finally, in the geometric shapes that we can work with, we have stepped walls. In this case, we've gone from masonry, stepped wall. And as you and I know, masonry walls and stepping, or masonry walls that are unreinforced, need to be very large in their width. I think it's a 3:1 ratio is normally recommended as your starting point, as for your width to height of your wall. So those are the basic geometric shapes. Now, we've already seen from the program that we can do concrete, and we can now see that we're doing masonry. The red is the masonry. This masonry is unreinforced. We've put a wee tick and a tick and removed those, so it's an unreinforced masonry wall. If we want to do reinforced masonry, we need to obviously step up and have the full version, not the power pad version. And this is this is a solid masonry wall. And as you can see, without the stepping or reinforcement, we're going to need a pretty thick wall. We're failing miserably here. So let's step forward and see if we have a reinforced masonry wall. Okay, we're now up to a 2.2 meter high reinforced masonry wall. One of the great things here is the ability to have this cavity with a cladding skin. If we go to the masonry, the way we generated that was very simple. We took our basic wall with the dimensions we defined earlier and say we have an outer skin and its thickness is 100, so therefore the fill cavity is 100. Now, the bricks or blocks are concrete blocks, group 2, category 2, and their mortar designation 12. Unit strength. The unit strength of the internal brick is not that important. It is covered to the reinforcement. What is important is the unit strength of the outer brick, because that is the compression face. This is the compression of your concrete. So as you go up and down, now reinforcement, we're going to put some wall reinforcement in, and we need to increase this, and we're seeing we're getting quite heavy reinforcement without much gain. So what I'd prefer to do is to come back here and make this a 215 outer leaf. And actually I turned off the cavity fill, so at the minute it was just sitting there as cladding doing nothing. So in my talking cavity filled, hey, it now works very well. So we actually probably would have got away in this case with the 100. But let's go up and say make it a 140 wall. Let's put in 10s at 200. You can also drop these wee lists. And then let's just for the fun of it discover how high this wall could go. So let's stretch it on up, and actually we were right on the bone, but it's not the wall that's the problem, it's the size of the base and sliding. So we'll ignore that for a moment, and we can see the wall itself is now failing. There we go. We could have gone out to 2.4 meters with this 140 wall. And the sliding, several ways of solving that. The most basic is obviously just to give it a bit more soil, a bit more weight. It's not going to slide. Now, the third or fourth type of wall is a wee bit abstract. It is possible. So I've done it. And that's the gabion wall. What we've done is we've gone for a concrete wall. So let's go back to wall data. Here we go. Our basic dimensions, we've asked for it to be stepped, 1,000 out, 1,000 down, 1,000 out, 1,000 down. And we've put a concrete density of 18 for our self-weight. But what we've then done is we've said no reinforcement. Well, we need to keep reinforcement in the base even though there is no base, otherwise it would just get annoyed, but it's not significant. But no reinforcement in the walls, and we put the concrete tensile strength to 0. That means it won't take any uplift, it needs its own static weight to hold it in place, and that proves our gabion wall will work. So moving on, that's material types. We're now going to move in to loading. I'm going to come back to something similar to what we had in the first example. We're going to have a taper, but we've got all these additional loads on it now. So, and it's failing miserably actually because it's exceedingly heavily loaded, and it's just for example. So let's look at the loading. What loads do we have? We've obviously put in an additional load from a soaping soil. That's very straightforward. We can have the soil at 10 degrees here, and we've even sloped the passive soil at 12 degrees. So here's the passive soil coming in at 12 degrees. We've also then got a water table, and we've moved that water table up to 1 meter above the base. To me, that's a good belt and braces, because even though it's going to be excavated and refilled and drained, I always like to leave a bit of water. But if you don't want to, you just pull that right down. Down comes your hydrostatic loading, and what you actually do is you put in a negative. So at the minute it's the top of the base space, so I'm going to say minus 500, and that just says, get out of my way. I don't have any hydrostatic. So that's removing the hydrostatic pressure. So I'm going to put that back on again just so that this is complete. The next loading we have are 2 or 3 point loads. You've got a point load on the top of the wall and point loads back on the wall. So the top wall point load on the wall, let's look at our loading. It's very simple. That's this load here. 50 kilonewtons at minus 150 in the center of the 300 wide wall, and it's a dead load. The next load is a 10 kilonewton load at 800 along the wall. So that is a soil load, and you can see its effect on the diagrams. And then after that we have this 35 kilonewton load at a meter back, and it's actually been applied. I tell a lie, this one has been applied on the negative side, so that's this load here that's been applied slightly down. So it's like a platform, a walkway, something has been hung off this wall and is giving a destabilizing overturning moment. The fourth load at 1800 back is another 10 kilonewton, and you can see that that one's coming in around here. Is quite nice. You can just go drag it down with your mouse, roughly 45-30 degrees, whatever, and you can see the effect of that coming in. So it's coming in at that point there, so it's coming back out to there, and we can see all that in the pressure diagram. Now, we also have applied a 10 kilonewton surcharge on top of the wall. I'm going to get rid of these line loads for a second. Make it clear. I have this 10 kilonewton wall surcharge is only from 1700 to 6.5, so it's some sort of building sitting back or some sort of transient load. In this case it's a live load. I'm going to take that off, and we're stepping back in our complexity. We still have this additional surcharge of 14. I'm going to pop that off, and we now only have the basic surcharge as the code requires. What we do have now is a horizontal surge force. You remember I said earlier we can have a horizontal surge on the wall for barriers which isn't part of the structural wall. So we can specify the force and its load, and that gives us a destabilizing. And we'll see in a minute when we have a physical projection like we had earlier, we can also put on a wind loading onto that component of the wall. So let's move on to our 11th frame, and here we are. We have our wind loading on our extended stem. Very straightforward, 1.5 kilonewton wind load. We've no other horizontal surcharge, but we also at this stage have gone for props. We've gone for a prop at the base. Turn it off. You'll see we have wall sliding. Turn it on. We have no wall sliding resistance. This is the prop at the base through the centroid of the base from an analysis point of view. Next we have the physical props, and I have a prop at 2 meters up, and because I put no spring stiffness, it is an infinite prop. It is infinitely stiff, so we get our typical diagrams. And if I just go to my drawing and I knock off the moment capacities, we get an enlarged applied moment diagram. We can see this effect of this prop here coming up, and you'll wonder, why is it starting not at 0? The simple answer is, from a soil point of view, that's the load, except we have this external load of 1.5 at 525 mil up is giving us our factored or unfactored overturning moment. So we've got a pre-existing moment from the wind load coming through into the frame. Now, coming back to this prop and tie, I said we can make it a spring, and I can make it a spring by giving it a value of 5 kilonewtons per to move 1 meter is nothing. 50 is nothing. 500 is still nothing. 5,000, and we're beginning and only just beginning to get an effect of this on the wall. It is beginning to affect the bending moment diagram, and only just. So that's 5,000, 50,000 kilonewtons to move the support by 1 meter. That is quite a large load. So there's our prop back in again. Now we also have something called ties, and ties are, to me, very rare, but they can be used, and this is an example of a 10 kilonewton tie at 400 down from the leading edge there, and 350 back at an angle of 20. So we're thrusting through at this angle, so some sort of rock anchor applied to the structure, again giving us the similar to the prop, but we have them isolated as being separate items. And we'll put our prop back in again. We have also gone one stage further with this frame, and we have on our soil data gone for layered soil, so the upper and the lower soil is different, and the lower soil is at an angle of 6 degrees, so we're banking back up here at 6 degrees on this lower surface, which starts at 1.5 meters up. So that is layered soils, and for that layered soil we can define all sorts of different materials. It's friction, it's base friction, density, submerged ratio, over consolidation at rest. Then we have the upper soil, and we have for the upper soil tension cracks, because it doesn't quite make sense to have tension cracks in the lower soil. Or does it? No, you don't give you tension cracks in the lower soil. It doesn't quite make sense. I didn't think so. And then we have the front soil. So we can even have this front soil, which is very, very small height, having a totally different set of densities and ratios. Now, we've looked at the external loading on the structure. The last thing we want to look at in this loading area is the bearing pressure. And the bearing pressure, we can, because we're working to the EuroCodes, you can have two sets of bearings pressures depending on different parameters set out in the code of practice. And believe me, it's quite scary, because it's something that a real soil mechanics expert will need to be working with. I would certainly, as a structural engineer, just be asking a geotechnical guy, what is my bearing pressures for M1 and M2 conditions. If you want to specify two conditions, you can just go M2 and a semicolon and put in the second capacity. So under the second capacity for M2 loading, your bearing pressure is 150. If you want the front and back to have different values, you can again put in a front. If not, 0 means they're the same. Instead of having sliding, you can put in a soil cohesion. So we have all these different soil parameters that are available to you. So now let's look at the loading again, and we're wanting to look at the loading with regard to the defaults, the factors of safety. Here we go. We're in our EuroCode format. So we're looking at our equilibrium and our A1s and A2s loads. And for your active, your tie forces, your surcharge, your base loads, and all the way down to nib passive and nib active if you really want to try and make that nib give you great benefit. And then some simple limits on the reinforcement and our factors of safety against sliding and overturning. Our minimum surcharge, the BS suggests 10 kilonewtons, and we've left it in there. I think the EuroCode has a similar value, but you can come in and stipulate what you want your base to be. And that gives you great scope. So next, I'm going to do some rail design. I'm going to take another wall, and I'm going to come back to the first one, and I'm now going to take a copy of that. So add a brief as a copy of this one. So I'm now in brief 12 of 12. Coming into my wall, I'm going to say no, it's 2.8 high, but we do have a 15-degree soil on the back. So 15 degrees soil, 2.8 meters high. Water table is at -500, so I'm going to say no. I like to be safe. I want to put in a 1 meter high water. So the first thing I want to do is to look at the sliding and overturning. So wall stability, it's okay. Sliding is not okay. So I either increase the length here and make it nice and long to grab a heavier load, which is quite long, or I think about saying, well, actually, let's put a prop in, put a prop at base. It's in a basement, yeah, maybe not with this sloping soil, or let's go and put a cohesion in for the base. So if I go to my soil data, I can say for the front I want a soil cohesion of 25, and therefore it's now satisfactory with that small cohesive resistance of the base. The choice is yours. I'm not stipulating or endorsing any of the different methods. I'm just trying to demonstrate. So now I've got my basic wall size. I'm probably happy at a 300. I don't necessarily know that I'd want to go down to 200. Well, with a 200 I need some more reinforcement, and I think I'd stick with a 300 base. If I want a nice slender 200 wall, everything's okay until I get to reinforcement, and 10s at 100 aren't working, so we would need to go to 10s at 12s at 100. What about 125? And we can see here the reinforcement. So let's look at our physical loading. What we're going to look at is the results here, and this shows us how we're actually doing our design. We are designing to EuroCode 7, so we are using all the different permutations. We are designing using these loading cases here. We're using design approach 1. The UK National Annex suggests you use design approach 1, and that is the design approach that we are using with these parameters on your geo plus structural A1 plus M1, then A2 plus M2, and A1 plus M1, and A2 plus A2, and A1 plus M1. So these are all the different loading cases we look at with the favorable and the normal surcharge loads. And then we come down to do our geotechnical design, looking at our results for our soil pressures and our virtual backs. And then, having got the geotechnical design done and shown that the wall is nice and stable and they're overturning or sliding, then we look at the wall design. So we're looking at the inner steel of the wall, the top of the base and the bottom of the base. So the top of the base is on the back soil, and the bottom of the base is the tension reinforcement on the front of the base. So that's your detailed design. Now, in all this, we have our defaults. So we can say what the A1, A2 factors are for all the different parameters. We have them for every single different possibility, but one or two of the values can't be changed in here. Now, what I'm going to do is I'm going to step back out of the retaining walls, and I'm going to talk about national annexes, because I mentioned that we work to the BS, the British, no, not the BS, the British National Annex. So if we move into MasterSeries customization and then into design codes, we will see that we choose a national annex. We can choose the default values, that's the Euro norm values, or we can walk through and choose the UK values. Now we cannot edit the UK values. These values for actions, favourable and unfavourable, your M values for your soil, your M2 values, your partial factors on actions, your partial factors on soils, these are all fixed because it's the UK national annex. What I can do is take a copy of the UK national annex. I'm going to choose the UK national annex as my default, which I'm copying from, and I'm going to call this UK one. We'll call it George and add new. So what that does is it takes a copy of, in this case, the UK. But now that we're in George, we can come along and we can say unfavourable, I fancy 0.55, and unfavourable, I fancy 0.35, and I fancy 0.3. Hopefully that's conservative. And then once I've done all that, I'm going to save these, and I'm now going to come back into my design, my retaining walls, load up my samples, doesn't matter which one. But what we have here is we have more control over our design. I can come along and say design code EC3 with the UK George set of values. So we now will find it in one or two little places we're using slight 5.5s. I think we played with the 5.5s and we put in 3s instead of 2.5s in one or two places. So we have played around with the values and made them applicable to ourselves. So if you are wanting to be fancy, you can do that. If you're working out of Ireland or France or Greece or even South Africa or Australia, you can put in your own interpretation of the nationally determined values. So that gives us great scope and flexibility in this program. So what's left? Well, we've been through the basic design process. That's pretty straightforward. We've been through the loading cases and the fact that we use design approach 1. The last thing I want to look at is this exporting and detailing and scheduling of the software. So we've done a design, a simple retaining wall, and we now want to export. I'm going to export the wall as U-bars and straights, which means we'll have a U-bar and then straights. So we're going to anchor it using U-bar, and we'll put a U-bar at the top of the wall. That's what I had turned on. U-bars and straights, but we will put actually a U-bar at the top, and we will then have some base reinforcement as U-bars and straights. And the length is the length into the page, as if I can't even show you how my hands are moving. It's not this 3 meters, it's not that 3 meters, it's the overall length of the wall as you look at it in elevation for the detailing. So I'm going to say we're going to detail this in 5.05 meter lengths. We're going to have some tolerances and minimum laps, and we will just export it. And first of all, let's load on AutoCAD. So let's export to AutoCAD. Yes, so there we are. There's my reinforcement and my front and back steel. As you can see, the overall length is going to be the 5 meters, so your bars are detailed out, and that's pretty straightforward and nice and clean. And there's your nice clean reinforcement with all your marks and your heights and your lengths. So let's just minimize that and come back and export the schedule. And this schedule, here we go, 8666. So 4.9 meter long bars for our straights B10s because it's 5 meters, less 50 cover, less 50 cover. All our U bars and L bars, I think they're all 21s or U bars, I believe. Yes, I did ask for U bars. So that's your reinforcement, and we can look at the weight, so we can see that we have 0.7 of a ton, 0.7 of a ton, and we can even see the shapes that were used, so 0 and the 21, so we can see the shapes that were used. So if we quickly jump back in and say, no, I want to use L bars and I want to use open links and straights, that'll be fun. And Alt turn it, and let's go for it, and we just do that. Schedule again, we'll not do the AutoCAD exporting. We will see that we get a lot of different shapes now, 21s, 11s and 41s, as well as the zeros. So what do those mean? Very simple. 41 is the open link, so that it makes life easy. L bars and our U bars, and then the 00 is the standard. So full exporting and everything is available. So that's covered the scope of the program, except for two things. And I didn't mean to come back out as far as this, sorry about that. Highways. We are able, as a design code, to also design to BD 3087 and BD 3703. Those designs themselves are, and loading is to this code and not to the EuroCode at the moment. So the BS 8002 loading with that. Naturally, you could design your masonry if you wanted to, but I think it's going to be more intelligent to be designing to 8110 and the BS not to have any masonry to worry about. So highways, and we now have our highways tab where we have our load factors for all the different loading combinations, and then we have our loads. A 175 kilonewton load in the Y direction at minus 500, and it is a dead load to 5.1. So 5.2 superimposed. HA loads, HB loads, and temperature loads are being stipulated. All of these that we need, any collision loads. So we can do the full bridge abutment design if we want to go the whole stage, or just the simple retaining of a normal soil adjacent to a highway and therefore to the highway rules. So that's totally available to you as well. Now, if I step back and step out of this program, I'm going to pull out my little electronic key, which made a noise, hopefully put in one that is just PowerPad, start back up the MasterSeries. Okay, just to test your MasterSeries license. So PowerPad fully licensed, PowerPad Plus not licensed, so this is the very basic. Just checking, those are PowerPad limits. Those are not part of PowerPad. Those are PowerPad limits, PowerPad limits, PowerPad limits. Yep, PowerPad limits. Limited, 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 unlimited. So the retaining walls is the PowerPad limited license, and everything else fine. So when I come in to retaining walls and I try and do a new file, PowerPad version, come up with my basic file. I can certainly do the extensions and things like that, and the sloping backs and water tables. When I click layered soil, I get nothing because I do not have layered soils in the PowerPad version. So that's limitation number one. Props and ties, they're turned off. All I can do is prop at base. So that's another limitation to the PowerPad. Loading, I have no additional loading. I just have the default surcharge and the additional surcharge if I so desire. Can I put a minus sign in? No. Reinforcement. Yeah, I can play around with reinforcement. I can do reinforced concrete. Masonry. Oh yes, I can do masonry. So if I have a masonry wall, what I cannot do is cavity reinforcement. If it's masonry, there will be no reinforcement in the wall. So that's another limitation. Piers, no, I'm not allowed piers. And lastly, it will not actually do highway loading. So the PowerPad version, it's still very, very flexible, but what you cannot do is additional loading, highway loading, piers, and layered soils. So finally, ladies and gentlemen, that only leaves me to say thank you very, very much for attending. If you want to contact me, it's very, very simple. It's just tommy@masterseries.co.uk. If you're looking to try the software, just log on and request a free trial application of the software. Let me see, you would just go to online quotation and just fill in your details and say, I want to try retaining walls and maybe the masonry as well, and I want a 30-day trial. Please, fill it in, send it off, and we will get you by return, hopefully within 24 hours, a free trial, a link to download the free trial of the software. Remember, it does not at this moment in time run on Windows 8 in the software trial version. The commercial versions all run on Windows 8. So ladies and gentlemen, I would like to just thank you very, very much for attending this webinar.